Hello and welcome to a video for day 113 of notes. You'll need to start with your own paper today, so have that out. You'll also probably want your calculator. I've only got this old one, but we'll make do with it. And you're also going to need this note sheet. It says day 113. Hopefully you have that available, so grab that as well. But if you want to start with your own notes, that'd be great. So again, we're going to start with, you can label this day 113. And we can call this exponential growth and decay. Which is definitely a topic you've heard of before, and it's just going to be kind of a new spin on it. Okay, but before we get into that, let's do some quick review, because we've done a bunch of new integrals and whatnot in the last few days, so I want to make sure we're all on the same page with that. Probably the easiest integral that you'll ever see, or derivative, is the derivative of e to the x. What's that? It's the e to the x, good. So then you knew that the integral of e to the x dx was also e to the x, plus c, of course. And we also talked about the derivative of ln of x. And what's that equal to? Good, 1 over x. And the integral of 1 over x dx, by the same token, has to be ln of x, but remember it's ln of the absolute value of x, plus c, just so we don't have any domain issues that come up. Okay, then some of the newer ones, we've talked about the derivative of a to the x as well, so it doesn't have to be an e as a base. But similar, it stays a to the x, just like it stayed e to the x, but what else have we got? We multiply it by ln of a. So then probably the newest integral we talked about was the integral of a to the x dx. What was that? Well, again, a to the x has to be involved, and since it's the opposite of the derivative, instead of multiplying by ln of a, we divided by the ln of a, plus c. And then the only other thing we talked about, we did the derivative, if I can fit it in over here or not, of log base a of x. And also similar to the derivative of ln, it's still a log, so you're going to have that 1 over x involved. But remember, there was also an ln of a down with it. Okay, so those are kind of the newer exponential, logarithmic, derivative, and integral formulas we're going to be talking about this year. I just wanted to do 2 more integral examples, just because we didn't get a lot of practice with that yet. What if I asked for the integral of 3 minus x times 4 to the 3 minus x squared? So all squared like that, not just on the x, dx. All right, when you see that, what's it kind of scream to you? Hopefully it screams you some. That's what it screams to me, so loud. What would you let u equal, do you think? Okay, you actually want to make it equal to the entire stuff in that exponent. So we're going to do 3 minus x squared. And the reason you want to make it equal to the squared is because when you take the du over dx, the derivative, what rule are you going to have to use? Right, chain rule. It's going to be 2 times 3 minus x to the first power, but still times -1. So if I make it equal to that square, I won't have to deal with a u squared up here. And the squared doesn't really mess up my derivative at all because it just causes an extra constant. And I want to solve for 3 minus x dx. So we would say that du over -2 equals 3 minus x dx. Okay, good. So now what's the substitution going to look like? Well, we're going to have a -1/2 out front times the integral. This will be 4 to the u, and the leftovers, we already pulled the -2 out front, so we just have the du left. So it's just going to be 4 to the u du. Okay, so then hopefully you can see that that's this rule right above that we just went over. That's going to be negative 1/2 times, it's going to be 4 to the u over ln of 4, good, plus c. And if you want to kind of combine stuff, we're going to end up with negative 4 to the, let's put the u back in, 3 minus x squared all over 2 ln of 4 plus c. Notice I don't need an absolute value on that 4 because it's a constant and it's a positive constant, so I don't have to worry about it not being negative or anything like that. So that'd be my answer. Makes sense? Of course it does. All right, one more, and then we'll get into the new stuff. Oops, black. All right, so let's do the integral of log base 2 of x all over 2x dx. All right, thoughts on what to do with this one? This one's a little weirder looking, maybe. Well, first off, that 2, anytime you see a constant, that's not really a problem because what can happen with it? We can move that out front. Okay, so picture this 2 is eventually going to just move out front in the denominator. Then what? Well, we have this log base 2 of x and this over x piece. But remember, when you take the derivative of log, you get an over x piece with an extra constant, but that's just a constant, so who cares? So let's do u sub again. And let's say let u equal log base 2 of x. So then what would du over dx be? Well, it's a log, so I know it's going to be 1 over x. So we have this extra ln of 2 with it. And I really want to solve for, if this is u, I just have a 1 over x dx left. So I need to move this ln2 to the other side. So ln of 2 times du equals 1 over x dx. All right, and then I think I'm ready. So remember, what's going to be out front? We have this ln2 coming out front because that's just a constant, but it also should be over 2 because I'm going to pull this 2 out of the integral as a constant. Okay, and then we're going to have the integral of u du, right? So it turned out to be a pretty easy integral to take. We're going to have ln of 2 over 2 times, what's the integral of u? It's u to the first. So u squared over 2 plus c. And just plug that u back in, and it's going to look like ln of 2 over 2 times log base 2 of x squared all over 2 plus c. If you wanted to, you could say that's ln of 2 over 4 times log base 2 of x, all that squared, plus c. All right, do you think you could change that in any way? Could you bring this 2 out front? No, you can't bring the 2 out front because it's not on the x, it's on the whole log piece. Can you think of another way to write the front? That would actually be the same as ln of the 4th root of 2. I wouldn't necessarily suggest writing it that way, but can you all see why that would be? There'd be a 1/4 out front. You could put that in as an exponent. 2 to the 1/4 power is the 4th root. Just some fun with exponents for your calculus pleasure. All right, so let's go on to the new notes, exponential growth and decay. So get out this worksheet and start looking at what it says. It says the quantity y grows or decays at a rate that is at any given time t is proportional to the amount present. Okay, well, anytime we talk about rates in calculus, what are we usually referring to? What's a rate mean? A rate is a derivative. So I'm going to say dy over dt, that's a rate. We can call that the rate of change of y. I just picked y to be, well, it says the quantity y grows at a rate, so that's why I use dy. So this is the rate of change of y. It grows at at any time t is proportional to the amount present. Okay, so I'm going to say equals k times y, and here's why. Y is the original quantity. That is the amount present. It's proportional to the amount present. So we need to have some constant of proportionality. That's what k is going to be. Constant of proportionality. Okay, so that's how to translate that sentence into calculus. A quantity grows or decays at a rate, dy over dt is the rate, that at any given time t, that's why it's with respect to t, is proportional to the amount present. So some proportion times the amount present. Okay, now you already know what this solution to this formula is, whether you realize it or not. And let's derive the formula. So if I start with dy over dt equals ky, what I have right here is a differential equation. So here's good practice. We're going to solve as a separable differential equation. Okay, so it's been a while since we've done that, but what's a separable differential equation? What's our first step? Remember, the first step is to separate. So I want my y's with my dy. I'm going to keep k with dt just because dt needs some friend. We could put k with the y too. So if I separate, multiply both sides by dt, I would have k dt. At the same time, I'm going to divide by y, so I could have dy over y, or I could write it as 1 over y dy. Okay, that's the separable part. What's next? It's the differentiable, which means I can take the derivative and the integral of it. So now we're going to take the integral of both sides. Once we separate, we always take the integral because we're trying to get y. Okay, what's the integral of 1 over y dy? Ln of y. Ln of the absolute value of y, right? What's the integral of k dt? Remember, k is just a constant like 5, so what would be the integral of 5? Be 5t. The integral of 7 be 7t. So this one will be kt. And we need a plus c. Let's just throw it on this side. Doesn't really matter which side we put it on. Okay, so we separated it. We did the differentiable part. Now we want to make an equation out of it. I want this to be y equals. So what could I do to both sides? I could exponentiate by e. So now we have the absolute value of y equals e to the kt plus c, all in the exponent. But if I don't want this plus c trapped in the exponent, how else could I think of that side? Well, using exponent rules, it could be e to the kt times e to the c, right? Because when I'm multiplying with the same base, I keep the base and add the exponents. So it's just kind of undoing that. Okay, now what's e to the c? Well, if c is a constant, e to the c would be a constant also. And we could leave it as whatever we want, but we could leave it as e to the c, but since it's just some random constant anyway, let's rename it, oh, I don't know, a. Let's call e to the c a, just some other constant. Okay, so now what have I got? I have the absolute value of y equals a e to the kt, because this is e to the kt times a now. I can put the a out front if I want. It's starting to look familiar. Okay, so absolute value, well, all that means is that this piece could either be positive or negative. So if I ditch that absolute value, I'd have plus or minus a e to the kt. And there's your friendly formula that we've seen many times before. Y equals a e to the kt, or some of you might think of it as y equals p e to the rt, PERT, just with different variables. Or if you remember from pre-calc, remember the one we used for population a lot, NOECT, n equals n sub 0 e to the kt. All of those are the same deal. But since we just derived that, the big idea is going to be that when you see those words, a quantity y grows or decays at a rate that at any given time t is proportional to the amount present. Rate proportional to the amount present is the key there. It just means to use PERT, right? Ease peas. Okay, let's do a couple examples. Back of that worksheet. Okay, first one. The rate of change of y is proportional to y. That means the rate of change of y is proportional to the amount present. Exactly what we just saw in the front. When t equals 0, y is 2, and when t equals 2, y equals 4. Find the value of y when t equals 3. All right, so that statement right there tells us to use dy over dt equals ky, that differential equation that we just talked about. But we also know that that really means we're just using y equals a e to the kt. So we don't really have to do all that calculus deriving that we did on the front. Now that I've done it once for you, you just know that when you see those words, use PERT. Okay, so we know a couple things. We know when t equals 0, y equals 2. Okay, so 2 equals a e to the k times 0. So what's that really telling us? Well, e to the k times 0 is just e to the 0. What's that equal to? 1. So it's telling us that a is 2. So now I have y equals 2e to the kt. And that should be nothing groundbreaking to you. You always knew that p in PERT, the thing out front, what's it stand for? The initial amount. That's all I'm telling you here. When time is 0, I've got 2. 2 is the initial amount. Good. Okay, now I also have this. I know that when y equals 2, k equals 4. Oops, sorry. When t equals 2, y equals 4. So I can plug that into my formula. 4 equals 2e to the k times 2. What's this going to help me do? Solve for k. So divide by 2. We have 2 equals e to the k times 2, or 2k. How do I get rid of the e? Take the ln of both sides. So I would have ln of 2 equals k times 2. So k is ln of 2 over 2. So from that, now I have a full formula. Y equals 2e to the ln of 2 over 2 t. Finally, it says find the value of y when t equals 3. So when t equals 3, what's y equal? E's peas, just plug it in. Y equals 2e to the ln of 2 over 2 times 3. And here's where you need your calculator. So this one's a little bit annoying because it's an old one. I'm going to have to use some more parentheses. For u, we'll do 2e raised to the ln of 2, oops, not x, 2 divided by 2 times 3. And if I have an old calculator, that has to be written like that so that everything in the exponents in those parentheses. New calculator, you've got a little bit easier because obviously it'll put that up on its own. At the end, I've got 5 point, always round 3 decimal places, 657. We don't have any units or anything, so that's all we can do. All right, so essentially this is no different than the questions that you did with this formula in pre-calc last year. So hopefully this shouldn't seem too bad for you. Let's do one more example and then we'll be done. The number y of bacteria in an experiment increases at a rate proportional to the number of bacteria present. There it is. Increases at a rate proportional to the number of bacteria present. As soon as I see that, I know dy over dt equals ky, which also means I'm using y equals a e to the kt. Okay, good. There are 35 bacteria at the start of the experiment. Okay, good. So it's going to be A. And after 3 hours, there are 120 bacteria. Our goal is to find how many are present after 8 hours. Okay, well, I know that there's 35 present initially, so I'm going to have 35 e to the kt. Just like last year, this is a two-step problem. I've got to figure out what k is first, even though my goal is to find it after 8 hours. So use what you know. You know when t equals 3, y equals 120. So I could say 120 equals 35 e to the k times 3. So we divide by 35. And we can check to see if that's a nice number, but remember you can't round until the very end. So if it's not nice, I'm just going to leave it as 120 over 35. And yeah, I don't want to use that at all. So we'll just say 120 over 35 equals e to the k times 3. Solving for k, so we're going to take the ln of both sides. So that'll cancel. So in the end, we're going to end up with k equals ln of 120 over 35 all over 3. Okay, so now my real formula is y equals 35 e raised to the ln of 120 over 35 over 3 p. Kind of gross, but it's all going to be calculator stuff anyways. And then I want to see how much is present after 8 hours. So we're just going to say y equals 35 e raised to the ln of 120 over 35 all over 3 times 8. Again, if you've got an older calculator, it might be a little bit more annoying to do, like I have right here. Newer calculator will make it a lot easier. 35e raised to the, I'm just going to write in parentheses, ln of 120 over 35 divided by 3, parentheses, times 8, parentheses. So everything's in the exponent, first piece times 8. And I end up with 935.484 bacteria. Good. Again, all just pre-calc. All right, now the second part where calculus maybe comes in a little bit. At what rate is the population of bacteria increasing at 3 hours? In calculus, when it says at what rate, what does rate mean? It means derivative. Okay, so I've got to take my formula from up here, find the derivative. So I'm starting with y equals 35 e raised to the ln of 120 over 35 over 3t. Kind of looks like an ugly thing to take the derivative of, but let's see what happens. dy over dt equals 35, just a constant, so we're going to keep that out front. Then we have e to stuff. What's the derivative of e to stuff? Well, it stays e to stuff. So e to the ln of 120 over 35 over 3 times t. And then what I have to multiply by the derivative of stuff, which even though it looks ugly, it's just constant times t. So it's just going to be times that constant. ln of 120 over 35 over 3. And I want specifically what's the rate that the population is growing when t equals 3. Okay, so evaluating that at t equals 3 would look like 35 e to the ln of 120 over 35 over 3 times 3 times ln of 120 over 35 over 3. Again, I plugged in 3 there just because it asked me specifically at 3 hours. Now you could plug that all into your calculator, it's all numbers, or use what you know. We already know after 3 hours there was 120 bacteria. Well, that's what I just figured out when I plugged 3 into this part. So this should all be 120, and if you plug it into your calculator, you'll see that it is. So now all I really have to do is 120 times ln of 120 over 35 over 3. 49.286. And if you wanted to do units, it'd be bacteria per hour. Okay, so now I think intuitively that makes the most sense of what you would do to find the rate. Rate always means take the derivative. I have an equation, so let's take the derivative and get it. But did anyone think of another way you could have done that? Well, the trickier, quick way was I wanted to solve for the rate. Didn't I have an expression for that already? Yeah, that's the rate. dy over dt equals k times y. Okay, well, we knew k was ln of 120 over 35 over 3, k times y. I want it specifically at 3 hours. Well, there's no t to plug in for 3, but there is a y, and we know when t is 3, y is 120. So if I just did ln of 120 over 35 over 3 times 120, let's see what we get. Oh, look, it's already on my calculator. It's the exact same thing. ln of 120 over 35 over 3 times 120. It's going to be our same answer as before. So maybe that's a little bit quicker, but a little tricky because you have to think of that. Now, if we didn't know that at t equals 3, y was 120, like if I asked what rate's it increasing at 5 hours, this wouldn't be all that helpful because I don't know what y is at 5 hours. I'd still have to plug it in here, get what it is after 5 hours, and then plug it in here, which is essentially the same thing I'm doing over on this side. So just want to show you 2 different ways to do it. Either's fine. Don't have to worry. You can do any way you want. Okay, so anyway, at this point, you can now also do problem sets 107. So in addition to what's been assigned already, do problem set 107. All right, email me if you got any questions. Good luck.